We know why we're here. Let's get the character fully implemented, most of the camera work done, and then we'll wrap up everything in the next episode. Also, if you are finding this video helpful, please subscribe, comment, or do anything you can to let me know that it has been helpful for you so that I can know what I can do to continue providing beneficial information to you all. That was a mouthful. Let's go in and finish adding the events to our player character. We can double click on the request look at to get our look at event here. And for this, we're going to use the find look at rotation, find look at rotation. And for this, we're going to use our get actor location and find look at rotation. So we have the start of our current location and the target of our target point. And that will give us the rotation that we need to look our character at this point. And then we can use set actor rotation. Set actor rotation. You can hook this pin into here, pass this value here, and I guess to really know that this one's working, we'll need some sort of mesh here. So let's click on our mesh, and under the mesh section, we have the skeletal mesh asset. We'll use this drop down, and you could use either of these. The cube and the skeletal mesh default are not that great. I'm going to go with the tutorial TPP, and if we head over to the viewport here, we can see it added to our character. I'm going to bring it down a couple of notches, few notches, many notches, and orient it to face the direction of the arrow, so 90 degrees that way. And finally, I'm going to set the animation mode to use an animation asset and set the animation to play to walk forward, just to give it a little bit more interesting of a look. So, returning to our event graph, we have our request look at, which should be coming from our player controller every frame with the target point of where our mouse is. And we are setting our actor rotation to look at where our mouse is, in theory. So let's give this a try. And you can hit Control B to return to, and that's B as in boy, bravo, bravo, bravo. And then Alt P to begin playing. And oh my God, that's not what we want. Okay, so we're gonna go into our spring arm here, and we are not going to inherit the yaw. Let's try this again. Control B, Alt P, there we go. Alright, our camera is no longer rotating with our character, and our character is facing towards our cursor. And this looks like everything is working pretty well so far. And we've still got our weird movement that is not correctly mapped towards the up and down. But overall, this is headed in the right direction. Oh. And finally, we'll want to add the request primary attack. We'll double click this and bring it in. And for the target point, I'm just going to do a draw debug point. I'll set the size to say 15. Color more interesting than black, and the duration 1 second should be fine. So we'll save this and Alt P, we can just play it in the window here, and look at that. Alright, we're clicking, the points are appearing directly where our mouse is. We can move away, we can drag, we can paint, we can draw, and it looks like our conversion from mouse to world is working nicely. Alright, we've got a pretty good baseline for our character here. They can move around in a weird direction, they can look at the mouse, and they can receive attacks on a certain point. So now let's fix the movement to be relative to the camera's position. I'm going to create a new function within our BP character, and I'll call it convert movement to camera relative. This will take in a vector 2D movement. Then we'll need our camera. We'll pull our camera in here, and we're going to utilize the vectors of this camera to translate our movement into the correct orientation. And that means we're going to need the right vector, and this will be our x-axis going left and right, and then the forward vector being our vertical up and down. And now with our forward and right vectors, we're going to want to translate the movement. We can split the struct pin, and we have our movement x and our movement y. And now this will be pretty simple from here. We want to translate the value of our x movement into the right vector. And we can do that by multiplying the two together. Multiply, drag in our right vector, and again, multiply the y to the forward. And now we have translated the right and forward vectors of the camera into our movement X and Y. And now we'll want to bring them back together. So we've got our right vector, and we want to add it with our forward vector to bring the whole movement back together. And we'll click on our function here and add an output as well. And this one may as well be a vector at this point. Camera relative direction, or movement. Camera relative movement. And we'll pop this in here, head back over to our event graph. We can delete this conversion. We'll no longer need it, as our new function will be doing the conversion for us. And again, I'm going to make this pure. We do not need execution nodes for this purpose. Drag the direction into the movement, and we'll drag the camera relative movement into the world direction. So we'll compile this, Alt-P, hit up, we're moving up, right, we're moving right, left, we're moving left, down, we're moving down. But one thing you'll notice here is that the speed does not match between left, right, up, and down. We're moving much more slowly up and down. And this is because our forward vector is pointing downward from the pitch of our camera view. Let me show you what I mean. Let's head into our convert movement to camera relative function here. And click on our return node and hit F9, or you can right click on it and the add breakpoint would be here. You can add, but I'm using F9 to toggle it. And now let's do this again. We'll play it, and then we'll move, and now we've stopped here on our convert movement to camera relative function. And now we can actually look at all the values that we're receiving here. If we look at the right vector, it's currently a y of 1. There's no x, there's no z. And then if we look at the forward vector, it's a mixture between x and z. It's pointed quite downward on our character. So when our character is moving, they're actually trying to move downward into the ground or more up, which is not going to work out depending on which direction we're using, W or S, up or down. Now to even this out is pretty simple. We just need to drop this Z value to where X is the only value in concern, and then we can normalize it. So let's do that now. We'll stop the game, move all this over a little bit. From the forward vector, normalize. We'll select the normalize, and we're going to do it a little bit differently here. Going to right click and break this link, and then we can right click again and split struct pin. We can right click, break this link, right click, split struct pin. And now we can normalize the forward vector. We can just pass in the X and Y, ignoring the Z value, and then pass this new normalized value in as our forward vector. So let's try it again now. Alt-P to play it. We'll do a move. We've stopped again. And now let's look at our return value here. It's 1 on the X, nothing on the Y or Z. So if we remove this breakpoint and return to plane, we can say continue the execution up here. Click that. Now our movement is moving the equal speeds in all directions now. Up, left, down, right. Our character is no longer attempting to move vertically into the ground when moving on the vertical axis. Now that you have an understanding of the core idea behind the foundation of all of this, I'd love to hear your feedback, what you might do differently, or what you just think about the approach in general. So leave a comment, and I'd love to have a discussion that we can both grow from. So now we have a pretty strong foundation of a top-down character, and while it's not really performing any actual attacks yet, we have all the data we need to actually perform those attacks. The implementation itself so far is relatively simple. We receive requests through our interface, and anything can act with that interface. In this case, it's our controller. The controller sends the request to do things, providing some sort of directive within that request, and we can choose to ignore it or adhere to it. In this case, we're adhering to them all. We're looking at things when it wants us to look at them. We're moving in directions when it wants us to move. And for the attack, we're just putting a point, just sort of a slight nod to the controller saying yes, yes. So now just to add a little bit more quality of life to this, let's repeat the steps that we've taken so far and create some new controls, a new interface, and then implement them again. Having done all this so far, I think you'd be pretty capable of doing it on your own, and I'd highly suggest giving it a try on your own before proceeding further into the video. What we're going to do is add camera controls. So we would need input actions for rotating and zooming the camera. And to show you what I mean by that, to rotate the camera would be rotating the Z axis. This would rotate the camera around the character to give different perspectives on the level. So this is the action you'll want to take through the rotate action. And then the zoom, to zoom it, we would just do the target arm length. So we can see now how this is affected. We've zoomed in. We can rotate the camera a little bit. We see we're at more of a 45-degree angle, viewing downward now. So you want to create input actions and allow them to drive the Z rotation of the camera and the target arm length of the camera. Well, of the spring arm, which is driving the camera. So see if you can do that, and then I'll continue the rest of the way. All right, let's add these camera controls. It's going to be a lot of the same stuff we've just done, just iterating through it again to really solidify our understanding. All right, let's get started with our input actions. Right click, input, input action. The first will be rotate, and we don't really need to do anything for rotate. Digital bool is fine here. My plan is to put it on Q and E so I can rotate left and right, and digital bool will serve that purpose just fine. We'll close this, right click, input, input action, and zoom. I'll open this up, and for this one I'm going to choose axis 1D float. My plan is to put it on the mouse wheel this time. So I'll receive values of that scroll amount as the mouse wheel is activated. And I'll close this. Now to add the input actions to our context. We have our IMC top-down context. We'll open that back up. We can collapse our move and our primary attack, and they're going to expand again when I do this. Oh well. Collapse them again. You know what? Well, okay. I guess we have to fill it in with something before it'll allow us to add another one. So I'm going to add the rotate here. Then I'll add the zoom. And for the rotate, like I said, I'm going to do Q, oh my goodness gracious, and E. So one of these will have to represent the negative of the two values. Q is going to be our negative for this one. Modifiers, negate. And because this is only a 1D, it doesn't really matter what you select here. It's not going to impact anything else unexpectedly. We just want to negate the value, so I'm going to leave these alone. And E, we don't really need to do anything. It's going to provide the value just fine as is. Then for zoom, click the keyboard. I'm going to try this. Mouse wheel. Yeah, look at that. How nice. All right, and now this is good to go. Save and close. Next, it's time for the interface. I'm going to right click, blueprint interface. This one will be called BPI_camera, and I'll go on and open this one up. I'm going to add two functions here, one for each of our actions, request rotate and request zoom. Both of these will take in an input of type float for the amount that we want to either rotate or zoom. I'll do the same thing for zoom, float, amount, compile, save, and our camera interface is ready to go. Next up, you know what it's time for, the player controller. I'll right click, look for our rotate input. We've got our event here, we'll select it, and when it's triggered, we'll want to activate the request rotate message. And again, this will be headed into our controlled pawn. This whole thing down a little bit. And for the amount, I'll just say 1, and we'll alter this as needed as we go forward. And the same thing again for the input of zoom. Get the event, request zoom message, controlled pawn as the target, bring our action value over into the amount, and these are good to go. Next stop, player character, well, BP character. All right. So, BP character. Now we've got a new interface to implement. So we'll do the same thing under the class settings, interfaces section, add, search for BPI, BPI camera. We can compile and check for our new interface action, request zoom, request rotate. Perfect. All right, so let's start with the request rotate. Got it pulled in now, and we're going to want to rotate, as I mentioned before, the Z-axis, the yaw of the spring arm rotation. Let's pull in our spring arm, and we'll say add world rotation. We'll execute from our event into this, and because we only want to rotate on the Z, the yaw value, we can right click the rotation, split struct pin, and pull the amount from the request into the yaw. So let's save this and give it a try. Oh, there we go. Kind of. I failed to negate the value, it would seem. Both directions are rotating clockwise. So let's check out our context here. Look at the E or the Q. It is negated. Oh, I've slipped up here. I didn't think we would need the axis 1D, but this proves that we do. I'm not actually using the value being handed down, I'm just hard coding that 1 in there, right? For the rotate, we're going to use the axis 1D float because we'll want to have a range of -1 to 1 to represent our rotation. So I'm going to save this. So we'll right click and look for input rotate. We've got our rotate event here, and we will get our controlled pawn and send the request rotate message. Pass in the trigger to execute this, bringing in the action value as the amount. And there we go. The rotation is working nicely, and our directional movement remains the same no matter how we're rotated. Down goes down, up goes up, and our character continues to look at our mouse. Alright, next up, let's implement the zoom. Let's double click our request zoom, bring this in, and similarly, we will use the spring arm component, and we're going to adjust the amount of the target arm length based on the incoming amount. So we'll get the current target arm length. I'll move this up here and bring in a plus to apply to this amount. Actually, I'll bring all this down. Maybe. Yeah, there we go. This will look nicer. Okay, perfect. And from the spring arm again, we will set target arm length to the sum of these values. And I'll double click the line here, make it a little nicer. So we'll play again, and we are zooming very, very little. So we'll have to adjust the sensitivity of it to get this feeling a little bit better. And something else that didn't feel right was that moving the mouse wheel up to zoom in was actually zooming out. So we'll want to update this in the context under zoom mouse wheel axis modifiers negate. And again, we're only working with a single value, no need to worry about the configuration of the negate. -1 becomes 1, 1 becomes -1. There we go. That feels more natural. Now let's head back into our player controller and create a new variable called zoom sensitivity. This will be a float compile, and I'm going to set the default value to 100. And you can adjust this more or less depending on your liking and what feels good to you. And we'll look at our zoom here, and dragging the zoom sensitivity in while holding control to get the value will multiply the action value by the zoom sensitivity. So dragging from the action value, search for star, use the multiply, and bring in the zoom sensitivity. The product of this going into our request zoom, save, play. Oh yeah, that feels much better. The only problem now is just about how jerky it is, and we can fix that next. So let's head back into our character, and we can modify how our zoom is actually working within the request zoom implementation. So instead of setting the target arm length directly, we'll create a new variable called, well, I was going to say target arm length, but that doesn't feel quite right. I'm going to call it target zoom. I feel like that gets the point across well enough, and it'll be a float. So instead of setting target arm length, we'll do this later on, and I'll go on and delete this. Well, bring it down with it. We will set the target zoom, and we'll right click, search for add timeline. We're going to add a timeline here to update the target arm length over time. Zoom timeline. We're going to bring the execution into the play from start. So once we have our target zoom, we can use this timeline to lerp into the zoom that we were looking for. So I'm going to double click on the timeline. I'm going to set the length, which represents how long this timeline will last, to 0.2, meaning the transition will happen over 0.2 seconds. I'm going to add a track of type float to represent our linear interpolation. With our graph here, I'll right click, add key to curve float 0. And this time represents when this key will hit. I want it to be on the very beginning at 0, and I want the value to be 0. Then at the 1.2 mark, we'll add another key, set this directly to 0.2 on the timeline, and the value to 1. So the value will go from 0 to 1 linearly over 0.2 seconds. So we'll close out of this, and we have our new track 0 here. And going back into our timeline, I'll actually rename new track 0 to zoom interp, and yeah, that should be fine. Close out of this, and now we have zoom interp instead of a more ambiguously named variable for ourselves. So now we can bring the spring arm and this target arm length addition over here, break that connection. On update, we'll want to set the target arm length, and we're going to interpolate from the current target arm length. Look for lerp linearly interpolates between A and B based on alpha. So we want to go from target arm length to our target zoom. So we can bring that over, use the getter, and pass this into B. I'm going to pull the spring arm up above now, drag this up a little bit, and bring the zoom interp into the alpha. So as the timeline updates, we'll get our value between 0 and 1 and updating our target arm length to that value. And finally, we'll have to use our target zoom as the base for the amount to be added to. So going through this, we'll get the request to zoom, with the amount. We'll add that amount to our target zoom and set it, and then begin the timeline from the start. Each update, we will interpolate the 0 to 1 value that we're receiving across the target arm length that currently is and the target zoom that we want. Let's give it a try. Oh yeah, works pretty well. There's a little bit of a chaotic beginning, but that's because the target zoom was currently at 0 as the default value. But otherwise, it zooms in nicely and smoothly. Now let's fix the issue from the beginning. We can say begin play, add this in here, bring in our spring arm component, get the target arm length, and set this as our initial target zoom. So we'll move the execution pin into the set, bring the target arm length into the set, and now our target zoom will begin at the same spot as the camera's spring arm is currently at. And we no longer have that weird dip in the very beginning as it tries to interpolate from 0 to whatever new arm length we want. At this point, the only issue is really that we can zoom way too far in and way too far out. But look at that! We have a pretty solid player character going now. It could use a projectile and a little bit of cleaning up, but otherwise it's pretty solid. And we'll do all that in the next episode. So subscribe, ring the bell so you don't miss it, comment, leave a like, whatever you like to do, and I'll see you in the next episode.